Hi, I'm Steve Sobek, the owner of amysflashcards.com. This is the fourth lesson in a series of videos on how to use the TI-84 graphics calculator. In our last lesson, we were using a graphing method to solve equations. And in today's lesson, we're going to review method 1 and then go on to method 2. We're going to go through 2 examples, and I think that's all you'll need. It's amazing how easy it is to solve either simple or very complex equations using these graphing methods. All right, so let's delve right into it. Recall that back in the last video we were looking at an investment problem. We invested $15,000. We were assuming that the money was growing at a rate of 8% per year, and we wondered how many years it would take for our investment to triple in value. Well, 3 times 15,000 is 45,000. So this was the equation that we came up with. And you may or may not understand how we obtained that equation, but that's not our concern today. My purpose is not to teach you anything about investments. Our purpose is exclusively to teach you how to use graphing methods to solve equations. So here's an equation. Now we want to solve it. It happens to be an exponential equation, and step 1 is to get one side equal to 0. So we endeavored to get the right side 0 by subtracting 45,000 from both sides. That gave us a 0 on the right. We need that for method 1. We need one side equal to 0. And then we graph y is equal to this expression that's on the left side. Okay, that's the function that we desire to graph. So going over here to the calculator, hit the y equal to button, you can see that I already have this function typed in. I've already established a suitable viewing window. By the way, lesson number 2, pretty much the main focus of that entire lesson was finding suitable viewing windows for various types of functions. And we went through the whole gamut of different functions that you'll encounter in Algebra 1 and Algebra 2. And so if you need to review that, go back to lesson 2. And then when we hit the graph button, we could see the function, and our focus of attention is right here. We want to find out, where does this graph hit the x-axis? Now we know the y-coordinate of that point is 0. Okay, but we desire to find that's a question mark, what is that x-coordinate of that point? That is the 0 of the function, that's the x-intercept, and that is the solution to our equation. Remember, the main idea was the zeros of this function are the solutions to the original equation. Now this equation will only have one solution. All right, so on the calculator, we want to come over here. We get out of the pencil mode and hit second, calculate, right here above the trace key. To find the zeros of the function, or in this case, the 0 of the function, there's only one, we choose number 2. So we hit the number 2 button, and we have to answer 3 questions before it gives us the answer. We have to establish a left bound, so we go somewhere to the left of that point and hit enter. And then we move somewhere to the right of that point, and let's see, it's prompting us for the right bound. Hit enter. So now the calculator knows that we're seeking to find the 0 of the function between these 2 boundaries. The last prompt is guess. It wants us to give a best guess. All right, so we hit the left arrow key to get somewhere pretty close to the intercept. Anywhere in between will do. And hit enter. And upon doing so, we have the 0 of the function. And that x-coordinate, that value right there is the solution to our equation. Okay, that is the x value that makes the y value a 0, and since our equation had a 0 on the right, that x value that made this expression work out to 0 results in a true equation. 0 equals 0 is true. And that value for x, 14.2749, made it true and thus is a solution. A solution is a truth number, a value for the variable that makes the original equation true. All right, so there's method 1. Now the only problem with method 1 is this equation that we graphed kind of lost a lot of the meaning. For example, the y-intercept is negative 30,000. What meaning does that have? None. All right, watch method 2, and let's see if you like this better. Okay, now let's talk about method 2. In graphing method 2 for solving equations, here we're starting with the same equation as before, but this time we don't try to get one side equal to 0, but rather we're going to graph two different functions. We're going to graph y is equal to just the left side of this equation, as you can see I have here, and then graph y is equal to the right side. This happens to be a constant function, a horizontal line, but it doesn't have to be, and it normally isn't, but in this case it is. And we graph both of these on the same coordinate plane. Once we have them graphed, and we have a suitable viewing window, our concern is not what are the zeros of the function. Our concern is where do these two graphs intersect. Because if we could find a value for x to this point of intersection, that x value has the exact same y value. It's the same point on both graphs. And if we could find an x value that produces the same y value, then both sides of your equation will have the same value. In this case, both 45,000. But it doesn't matter what it is. If it's 5 equals 5 or 6 equals 6, as long as it's they're the same number, then it's true, and any value for x that makes the equation true is a solution to the equation. All right, and it's very easy to find, as you'll soon see, it's very easy to find those points of intersection. In this case, the point of intersection. So over here on my graphics calculator, you can see that I have the functions already typed in. And my viewing window had to be adjusted, of course, since we want to know when. We have a horizontal line up there at 45,000, so I have to certainly go a little bit above that, so I went up to 60,000 on the y-axis. And when we hit the graph button, we see the two functions. And we care about where these two lines intersect. That is the focus of our attention. All right. Now, to find that point of intersection, we hit second, calculate, and you could probably guess. All right. We're not using 0 like we did with method 1. We're not finding the zeros of the function. We're trying to find a point of intersection. That's number 5. So hit the 5 button, and like before, there's some prompts, there's some preliminary questions that you have to answer before it gives you the point of intersection. All right, notice the first prompt is that the first curve? It's blinking, it'll be blinking on one of the two functions, and it's asking, is that one of the curves that you want to find the intersection of? You see, it's potentially possible that you have 4 or 5 different functions graphed, at the same time, and it wants to make sure that it's going to be using the appropriate two functions for finding the point of intersection. So obviously, yes, that is the first curve. So we'll hit enter. Now it's blinking on this red constant function, and it's asking, is that the second curve? Yes, so we hit enter, enter. And finally, it's asking for the best guess. See, sometimes graphs will hit multiple times, and it wants to know which one are you going after. So since there is only one point of intersection, we really don't have to get very close to it. But notice I'm hitting my right arrow key just to get you in the habit of getting close to that point of intersection. We're going after this guy over here. So hit the enter to accept that. And lo and behold, it gives us the point of intersection. And notice that that is the same x value that we had before with method 1 when we were finding the zeros of the function. Of course, that was the y value was 0. All right. But I kind of like this method because the functions are just teeming with meaning. The red function, y equal to 45,000, shows our goal. Let me get my pen operational here. The y-intercept of the blue function, that represents the initial amount of the investment. Every point on this graph, every positive value, of course, the domain of the variable, is positive values for x. So these points are irrelevant down here. But all positive values for x, all of these points have meaning. If we jump into the table feature, let me do that quickly. Second table, and fire in some values for x. Okay, after 0 years, I have $15,000, the initial amount of the investment. After 1 year passes, I have $16,200. 3 years, I have $18,000. 4 years. You could see that every point on this graph, okay, 4 years, I have $20,400. Okay, so 4 years, that'd be this point right here, I have 40,000. So the graphs have so much more meaning when we use method number 2. And so I kind of lean toward that method. Okay, and so that's it. Second, calculate, intersect, first curve, second curve, basically enter, enter, and designate the best guess somewhere close to this point here. And it gives you the coordinates of that point, and our solution to the equation is only the x value of that point. Only the x value, not the y. The y value is, what both sides are going to become when we use that value for x. You have 45,000 equal 45,000 in your equation. But that's irrelevant. Our solution is the x coordinate, okay, which would be, what did we say, 14.3 years? 14.3 years. Our investment has tripled to $45,000. All right, there's example number 1. That wasn't, see how easy that was. We'll use a little bit more complicated equation for example 2, but I think you'll find it easy and do well with that as well. So let's move on to the next example. All right, here we can see the next example. We're trying to solve this equation. It's more complex than what we had previously. Fourth degree polynomial equation. Neither side is equal to 0, and we're not going to make either side 0. We're going to use method 2, the graphing method 2, to solve this equation. All right, so we're going to graph two functions. Y is equal to this left side, as you could see right here, and then graph y is equal to the right side, as you could see right here. So let's go over, hit your y equal to key, and we'll have to get rid of the existing functions. So let's go up here and hit the clear button, hit enter, clear, and then go back up and let's type these functions in together. You can type along with me. 0.1 x, here's your exponentiation right here, x raised to the 4th power. Now I need to get out of this exponent. It's blinking up here beside the exponent, so I need to hit the right arrow key one time to get out of the exponent. Minus 0.6 x raised to the 3rd power. I'll get that cubed from the math menu, number 3. Plus 3x minus 3. All right, hit enter. That's the first function. And the second function, in parentheses, we have 2/7. 2 divided by 7 times x, and we square it with this button here, squared, minus 2x. No, minus 2. Sorry about that. Delete. All right, remember in the earlier videos we showed you how to edit, delete, insert mode, and all that. So if you're a little bit shaky on your ability to edit these expressions, then go back and watch my first 2 videos. All right, now for the viewing window, why don't we start with the standard window. The standard window ranges from -10 to +10 on both the x and y axis. And so the fastest way to obtain that is to hit the zoom button. And you could see number 6 is our standard window. So hit the 6 button to choose that. And here the blue function would be our quartic function. There we are. And there should be a parabola coming up pretty soon here. Okay, we know that second-degree polynomial functions are parabolic. And there we are. That's not too bad of a viewing window. Maybe we could adjust that a little bit. See, 1, 2, 3, 4. Maybe let's go from -5 to 1, 2, 3, 4, 6. This 7. -5 to 7 on the x-axis. Hit the window button. And for the x values, let's go -5. For x max, let's go with +7. And hit the graph button again. And here we have a nice viewing window. There's our parabola. And how many points of intersection do we have? 1, 2, 3, 4. Now, should we be concerned that maybe there's more outside of the current viewing window? Because after all, in my earlier videos, I taught you to be very wary of what's beyond the viewing window. Other things could happen. But we also talked about having a very thorough understanding of the different types of graphs. And we know that a 4th-degree polynomial function will change direction no more than 3 times. And see, it's changed directions once, twice, 3 times already. It will not change direction again. We know that it's going to be shooting up for the moon for both extreme values, very negative or very positive values of x. All right, no changes. The parabola, of course, we know what a parabola looks like, and we know that parabolas don't turn around and come back down or loop over. And, all right, that's all the points of intersection. Our understanding of a thorough understanding of all the different types of functions that we covered in lesson number 2, helps us to have confidence in the current viewing window, knowing that we only have 4 solutions. Now, how do we find that point of intersection? All right, well, it's second, calculate, and sure enough, number 5, intersect. So we'll choose number 5. It's blinking on the blue graph right now, wondering, is that the first curve? And certainly it is. I only have 2 functions graphed, so it's going to be enter, enter. Yeah, it's blinking now in the red, so my curve, accept that as the second curve. And I'll hit the left arrow key since I'm first going after this point right here. Hit enter, and let's write down the first answer, negative 2.228. Let's go to 4 decimal places, 83. And we want to next go after this. By the way, do we care what the y value is? No. Well, no, we don't. You know, all we care about is what x value makes the y values the same. It doesn't matter what they are, okay, because as long as it makes them both this, negative 5.8, negative 5.8 equal negative 5.8 is true, and thus that x value that made the equation true is the solution. He is the solution, the x value. We're not concerned about the y value in this application. Okay. All right, let's go after the next one. Second, calculate. Number 5. Again, you could hit the down arrow key and to highlight that and hit enter. Either way, it's faster just to hit the 5 button. And again, first curve, second curve, so it's going to be enter, enter. And then best guess, this time we want to hit the right arrow key to get over here in close proximity to this next point of intersection. Hit enter to accept that. And let's go ahead and write down this next point of intersection. Okay, right here we see 0.3536. 0.3536 whenever we're rounding to 4 decimal places. All right, I suggest you pause the video and get the next 2 solutions on your own, and then restart the video and watch me do it and see if you got it right. All right, now that you've restarted the video, I'm going to go ahead and hit second calculate, number 5, intersect, enter, enter, accepting the first curve and second curve, and then hit the right arrow key to move close to this next point of intersection. Hit enter to accept that as it's prompting us for the best guess. So I'm pretty close right there. Hit enter, and then it shows me my next solution. Okay, 2.2612. All right, and then the last one, second calculate, number 5, intersect. The first curve, yes. Is that the second curve? Yes. Best guess, let's move off to the right until we get pretty close to that point of intersection. Pretty good. Hit enter. And when you see the word intersection here, then that x value beneath that word is your solution to the equation. 5.6135. All right, so that wasn't very hard, was it? Very complex equation. I wouldn't have wanted to solve that with factoring method, although I certainly want you to know the factoring method, and you know it has its uses. But in terms of you know, if you're an engineer out in the field, you know, your typical problem is not going to result in an equation that's going to be factorable over the set of polynomials with integral coefficients. It's actually very difficult to make up problems that are factorable in that way. But in the real world, this method would find those solutions for you, this graphing method. So this is the second of the 2 graphing methods. So let's go back and type in those values for our solutions. Okay, so let's go ahead and record those 4 solutions. Notice that we're just writing down the x coordinates of those points of intersection. In this case, we had four solutions to this equation. In quick summary, what is method 2, graphing method for solving equations? We graph y is equal to the left side of the equation, as shown here. Graph y is equal to the right side of the equation, as shown here. Graph them both on the same coordinate plane, and find where they intersect with second calculate number 5, intersection. First curve, second curve, best guess. Go through all 4 of them, and you'll have all 4 solutions. The x coordinates of those points of intersections, those are the solutions to your original equation. All right, pretty easy to do. All right, now there's a lot more to using the graphics calculator, the TI-84, and I plan to have quite a few more instructional videos on using this. You'll be able to access all of my videos at this website, amysflashcards.com. So I hope you visit and see what else I have there. Many flashcard-like drills for practicing not just math, but geography and vocabulary, music and Bible. And also I welcome your comments and suggestions. So here's my email address. I hope to hear from you. I hope this lesson was helpful to you, and I thank you for joining me today.